Am I audible?
Yes, sir.
Okay. So today I'm going to discuss about different controller that I just started my session. I just started my session in my last class of discussion of different controllers for power converters. Okay, so today I'm discussed about type controllers. Okay, so what is type controller? If you see in my last discussion, so where you can understand that I discussed about PI, then PD, then lead, lag. Okay, so then PID. Okay, combined of all those controller and your converter, and finally we can check their response, okay, in frequency domain. So today I discussed about type controllers. Type 1 means, you can see from this from the diagram you can understand, sorry, from the transfer function you can understand it's an type 1. It is written means it is behaves like a PI. It's an only PI controller. Okay, it's not like that it's the transfer function of type 1 controller. Okay, so normally we know in control system type means how much poles are there in origin. Okay, but in power electronics software designing, so type controller is not like that. Okay. So it is type 1. It's basically it's an PI controller. Okay, and your type 2 is cascading one PI controller that with the lead controller. Okay, so it's a transfer function of type 2 controller. So you can see that PI controller means one pole at origin. Okay, so and you are adding some lead controller. Okay, so that a, okay, so where your a gain a equals to sorry, a is positive and omega equals to, means first of frequency, that omega equals to in between omega of z means zero frequency and pole frequency. Okay, so here you can able to understand that transfer function of type 1 controller. Okay, so it's your circuit, you can say like that, compensation structure of a type 1 compensator structure, a schematic diagram. Okay, how it will look like. One integrator is there, you can see that one integrator is there. In type 2 compensator you can also see that figure. Okay, that figure you can see the type 2 compensator schematic. Okay, that was two indicators. So that bowl is there and that zero. Okay, that combinations are there already. So similarly you can see the structure of type 3 compensator. Okay, so type 3 compensator, you can see the structure and the diagram, that means circuit, compensator circuit diagram also given like that. Okay, so I think you are able to understand that structure, basic structure. So then you know that pole locations are given. So gain, what is the value of gain that is given. Okay, from that op-amp structure, gain, omega z, the zero locations, pole locations also be given. Then your mean value. Okay, that means omega, that mean value of two poles. Okay, then type 3 controller, then you can see the type 3 compensator or controller, you can say like that. One pole at origin and one pole at origin cascaded to lead controller. Okay, so two lead controllers are there. So they are cascading each other. Okay, so two lead controllers are there. So sometimes what happens that zeros. Okay, that here you can see that omega z1 and omega z2 both are in distinct value. Okay, so they are not situated in a single position. So if sometimes what happen, you can see in my later slide. So where I have assumed that both of the poles are situated in same place and both of the zeros are also placed in a same locations. Okay, so that is another
Sir, PPT
consideration
is
that
not
I
visible, sir.
yes, what happened?
PPT is
Hello,
not visible, sir.
it is not
Hello.
visible.
No, sir, it
Hello.
is not visible. Because of network issue, I guess, from your end.
Okay, it may be shown. Okay, so all of you are not visible, or it is happened for only some
All
of
of
you.
So all
It's
of
not visible.
all of
It is not visible.
It's not
Visible,
visible,
sir.
sir.
Now visible, na? Teja, is it visible now? PPT is visible
It's not
now.
visible, sir. It's showing in the small screen, sir. It's a very small screen. Can't able to read that.
Smart grid.
Small screen, sir. It's coming like small screen.
Okay, okay. Is it full screen now?
No, sir. Maybe network
Is it full
problem from
screen?
my side or your side. We don't know.
It's not in the presentation
In
mode, I
my
guess.
side. No, no. Right now, I think it is in full screen. Now I have made it full screen. Is it visible now?
no sir, no one can see.
No, sir.
It is not visible. That's right. Is it visible now?
Yes, sir.
Now, sir, it is.
Now it is visible. Okay. Okay. Okay, so here you can see the structure of the type 3 compensator and transfer function. Okay, sorry, and transfer function. Then you can see the locations of zeros. Okay, two zeros are there. Okay, then two poles you can see. Okay, means it's a lead controller with an pole at origin. Okay, basically type C compensator in power electronics. So who is inventor of this concept? Okay, that is it's a Venable. Okay, that concept was invented means this special type controllers was invented by Sir Venable in 1983. Okay, so if you want to more about the type controllers, okay, you can make a Google search. Okay, type 3 compensators. So you can get lot of documents. Okay, on it. So you can follow that one. Okay, and you can also follow any of the standard books. Okay, no problems. You can follow Ned Mohan books. Okay, so that is also mentioned over there. Okay, so here you can see that structure is given that type 2 compensator. In this structure, the two poles, two zeros are considered in the same place, and two poles are considered as the same locations. Okay, so that's the common structure. So for that one, we are considering that omega p1 equal to omega p2 equal to omega p. Okay, that is your consideration. Then omega z1 equal to omega z2 equal to omega z, another considerations. Okay, so I think you are able to understand that the basic description of type compensator. Then what is your key factor approach that I am telling you that tuning of that type controllers. Okay, tuning of that type controllers means type 1 controller or type 2 type 3 controller. So you can follow the method of k factor approach. Okay, that method was invented by Venable, that I am telling. So they have actually he made the tuning by using that k factor approach. Normally what happened in other controller, other basic concepts of the controller like PI controller, PD controller, PID controller, okay, any of the basic classical control type. Also the type controller, also the classical example of a classical controller. So in all those controller, you have to follow different standard method like ZN method means Ziegler-Nichols method. You can also do the frequency domain studies. Okay, but in type controllers you are also using different method, but normally if you use the K factor app, so you can smooth design, okay, and you can smooth and easy and simple design of type controllers. Okay, so what are the consideration? Okay, so the K factor, you can say like that. The first you know about the definition of K factor. The K factor is defined as the square root, okay, as the define of the square root of the ratio of the pole frequency to the zero frequency. Okay, that in my last class we are considering na. So that root under pole frequency by zero frequency. Okay, so that some factor was there. I think you are able to understand. Can you remember those one? So where I have written like that root under this value, root under GC0. Okay, you can see that the value of GC0. Okay, that root under FP by FZ. Okay, in K factor approach, that means FC. You understand that value, that FC value. Okay, that FC value. FC value equal to another thing you can write down that it was given that root under FP by FZ. Okay, that was discussed in my last class. Okay, so you can say like that, that pole frequency to zero frequency for type 2 controller. So you are making that K factor is the square root of the ratio of the pole frequency to the zero frequency for type 2 amplifier or compensator. You can say like that, or the ratio of double pole frequency, or the ratio of double pole frequency to double zero frequency in type 3 type 3 amplifier. Okay, so it is given like the double pole frequency to double zero frequency at type 3 amplifier. Okay, so and then you can say like that for type 1 amplifier, you can say like that K value is 1. Okay, so type 1 compensator K value is 1, and type 2 you can say like that, type 2 it was and for type 2 amplifier you can say like that has a 0 at f by k and a pole equal to k into f. Okay, so that is considerations of the frequency of f with the geometric mean. You can say like that, it's a geometric mean of zero frequency and the pole frequency. Okay, it's a geometric mean, and the peak phase boost from pole zero pair at the frequency f. Okay, you are getting maximum value of that possible phase boost is 90 degrees. Okay, it was there 90 degrees. Then type 3 amplifier, you can say like that, for type 3 amplifier has a double zero at f by root k and double pole at root k into f frequency. F is zero, again it is called geometric mean of the zero frequency and the pole frequency. The peak phase boost from pole zero pair, okay, occur always that frequency f. So I am showing you that how that f is coming that maximum value. Okay, so maximum possible frequency of phase boost is 180 degree. So here you have choice for the type compensator. Okay, so type 1 amplifier normally used for no phase boost, basically only is behaves like a only PI controller. Okay, then type 2 amplifier is normally used for that phase boost is there around less than 90 degree. Okay, so where you have used for type 2 compensator or type 2 amplifier. Okay, so here you have used for the type 1 amplifier. Then type 3 is normally used for where the phase boost is less than 180 degree, maximum 180 degree. Okay, so these three purposes are there. So basically we are using type compensator. So basically why they are important, basically in boost converter or buck boost converter, you see the dynamics of both of the converter. So where you can understand some non-minimum phase problem. Okay, due to presence of this non-minimum phase problem, unnecessary delay is there. Okay, so unnecessary phase lagging is there. So you have to boost up the phase. That's why you have to introduce some of the new type of controllers. That new type of controller is type controllers. That can give you inherent capability. That controllers having inherent capability to boost up the phase of that converter. Okay, so here you can see the derivations where you can say like that boost equal to phase boost equal to which means phase boost, okay, equal to tan inverse A minus of tan inverse 1 by 4. Okay, so as a trigonometric identity, you know that formula, the tan inverse x plus tan inverse minus 1 by x equals to 90 degrees. So you can substitute, so 1 and 2 equations, so you can substitute in that equation. Finally, you will get that A value, A equal to coming tan, okay, within angle, okay, that boost by 2 plus 45 degrees, that is coming. K factor relates the amount of phase boost required type to amplifier to achieve the desired phase movement. So your agenda is to find out your desired phase movement. So how much phase boosting is there? You can see that it is 270 degree and maximum will goes around 180 degree. So minus 270 degree plus or minus, sorry, minus of minus 180 degree. So it is coming 90 degree. Okay, so that how much phase difference may be possible for type 2 controller. It is derivation of a type 2 compensator. It is written, so derivation of a type 2 compensator. Okay, so your boosting is there, your boosting is there 90 degree. Okay, so your boosting is there 90 degree. That means that position. Okay, phase boosting. So if you see the gain plot, so you can see that logarithm gain is there. So one pole at origin, here you can see that one pole at origin. So that pole contributes minus 20 dB per decay. Okay, that minus 20 dB per decay it is coming. Okay, so two frequencies are there, that 8 by k. First it is your zero frequency, and what is your pole frequency, that k8. Okay, and what is your f equals to geometric mean of your pole frequency, sorry, of your zero frequency and pole frequency. So f equal to root under fk into kf. So kk cancel each other, root under f square. So it is gradually coming that f. Okay, so we will get maximum phase boost at this point. Okay, so in case of type 1 reference, so type 1 there is only one pole at origin, nothing cascading with that controller. So you can see the direct, okay, that direct slope of having direct slope is there. Okay, having direct slope is there. So one pole at origin, so it's slope with minus 20 per decay line. Okay, that is there. So that is difference. So k gain is there in type 2. So difference is there. At A, you will get the phase boost up to 90 degree. Okay, so it is started from to minus 270, now it goes up to minus 180 degree. So you can get maximum 90 degree. Okay. So it is your frequency domain analysis of type 2 compensator. Okay. After that, we can go for the derivation of K factor approach. Okay, K factor approach for type 3 compensator. So type 2 compensator is your one pole at origin and one lead controller, okay, that cascades with your integral controller. You can say in single input. So in case of type 2 compensator, two lead controllers are there. Another consideration is there that these two lead controllers having the same pole, okay, and the same zero. The poles, all the poles of the lead controller are placed in the same locations, and all the zeros of the lead compensator are placed in the same locations. Okay. So that's why what happened. So if you draw the Bode diagram, so you know that one, you know. So you know that it's a transfer function. Okay, transfer function of the type C compensator. So one poles is there, or one pole is there. That pole is located at the origin. Okay. So due to place at origin, so minus 20 dB by decay, it will decreases like that way. So it is gain is there. Okay. So in gain plot, so you can see, if you refer to your type 1 controller, so you can see that the gain is 90 degree. Okay, so minus 180 degree, sorry, minus 20 degree per decay line. And you can see what is your whole zero location. Zero location is always there f by root k. Okay, so in type 2, type 3 controller, the zero location you are considering f by 2k. Okay, then what happens here, you can see that it is minus 20 dB per decay line. Then two zeros are there, two same location zero. Okay, so two same location zero are there. So due to the presence of the same location zero, then what happened? 1 0 will nullify. Okay, here you can see that 1 0 is there. That is nullify that minus 20 dB per decade. So it is coming 0 dB per decade. So another 0 is there that can provide you plus 20 dB per decade. So again it will rise up. Okay, again it will rise up with plus 20 dB per decade line up to which portion? Up to the core location. Your core location is f into root k value. Okay, f into root k. So at that point, what happened? Then two poles are there. So one pole. So two pole means that omega p. Okay, that omega p is there. Okay. So that omega p first nullify that minus 20 dB per decay. Okay, so the plus 20 dB per decay. So again 0 dB per decay line is there. Then another pole is there. Okay, so that pole may contribute with plus 20 dB minus 20 dB per decay line, and it will follow the parallel. Okay, and it will follow the parallel line of your type 1 reference, and that value is called K. Okay, that K reference values is there. So here you can see that how much deviation is there. That phase at point F, that phase deviation is up to minus 272 beyond nearer to the minus 90. You can see that value, it is your minus 90 value and it is your minus 270 value. Okay, so it is started from here. Okay, then it is try to rise up to that position. Okay, then again it is come back to that value nearer to minus percent. So it is nearer to minus 90 degrees. That's why you can say like the maximum 180 degree phase leading is possible. Okay, phase leading is phase boost is possible in type 3 compensator. So what is your phase boost? So your phase boost value is that root k minus tan inverse 1 by root k. Okay, the zeros here, the zeros and the poles are coincide each other, so the phase boost is twice in your type 3 compensator. Okay, amplifier. So boost is your what? That boost is equal to the 2 root under k inverse minus tan inverse 1 by root k. So incorporating the trigonometric identity given in that form, so we are adding, so you know the formula, that trigonometric identity already given. So finally we calculate the value of k factor, k value in type 3 controller is tan within bracket boost by 4 plus 45 dB, then whole stop. Okay, so that is your k value for your type 3 compensator. Okay, now we have used that method for designing the type compensator for boost converter. So you know that from the structure that the equations are there. Now from the structure you can understand that value of you can understand that value. Okay, so that diagram is there. Okay, that all the diagram is there. So that amplifier diagram means here you can see RC values are there. Lot of RC values are there. So you have to calculate those values. So some standard procedure is already given. Okay, already given. If you can also analyze. Okay, you can also synthesize the circuit. So you get that value. So you can get that value. The subsequent states, okay, all the states are given. Okay, so from the resistor, that R, known capacitor, farad, so all are given. That F equal to the chosen crossover frequency, is the amplifier gain at that crossover value. So K equal to K factor value. So subsequent states are already there. Okay, for type 1, so K equal to 1, the structure, so that amplifier structure, so you can provide that one. K equal to 1 and C1 equal to 1 by 2 pi f g into R1. If you replace all those values, so if you have those values, you can replace them and you can find out the transfer function of your type compensator. Okay, then subsequent steps are there for type 2 compensator. Okay, so K values are already there. Okay, 10 value, you know that value of K equal to 10 of boost by 2 plus 45 degree. Okay, then what is the value of C1? That C1 is given C1, C2 and R2. So from the figure you can also understand the value of C1, C2 and R2. So from the figure, okay, so you know that value of C1 is there. Okay, C1 is there, C1, C2 and R2. Okay, that if that all those values are available, so you can easily find out the transfer function. Okay, so you can easily find out the transfer function of type compensator, type C compensator. Similarly, the type C compensator, you are using the subsequent state, okay, that K value, then CQ, C1, okay, R2, R3 and city. All those values are there. Okay, and you will easily find out all those values of C1, C2, R2, R3 and C3. Okay, so you can close there and you can find out the transfer function. So here I have considered one example. Okay, so the that input resistance working with type C compensator for boost converter. Okay, so input resistance you have considered input resistance R1 equal to 10k, then C2 equal to 1.15 microfarad, crossover frequency 500 hertz, phase boost equal to 70 dB. Okay, subsequent steps of designing type C compensator are follows. Then you can find out that other values. Okay, so k you can find out equal to 10 boost by 2 45 plus that is the square value. Okay, so k value you can calculate. Then C1, R2, then R3 and six. Okay, final you are able to find out all those values and finally you can calculate if you place them. Okay, if you are able to place them, so you can calculate all the values. So place them, so you can get the transfer function of type 3 controller. So from this transfer function, you can from this transfer you can see that on pole at origin, that is the denominator. Okay, denominator of this gain value and the numerator value you can see two zeros are there. Okay, two zeros are same location, two poles are same locations. All are there. Okay. Then you know the small signal modeling of boost converter. So I'm not going to discuss this again. So if you have that transfer function of boost converter, okay. So you know that from the small signal analysis, the generalized transfer function, okay. So it is your generalized transfer function. Oh sorry, it is your generalized transfer function of boost converter. Okay, content to duty ratio transfer function, and that this is zero. Okay, that zero location for left hand plane. Here you know that boost converter having right hand plane zero, so it's a problem of a non-minimum phase. Okay, that's why the negative sign is there, and it's in numerator. Okay, sorry, it's in denominator. So you know that all those values of gain. Okay, zero values. Okay, the zero value location, then omega zero. You okay? So all the values are already discussed. So I am not going again. I'm not repeating that portion. So you can cross check it, okay, from your side, and let me know if there are any problems are there. So you can calculate. Okay, so prove that value, that parameters are given in table. So if you put those values, so you will get you will get the final transfer functions. Okay, the final transfer function of boost converter. So here you can use that. Here you are able to use. Here you are able to use that. Here you are able to use that type compensator that you are that means sensing, or you are sensing the output voltage. That output voltage is your V0. Then you are given that reference value Vref. So after differential amplifier, so you passing to that error signal to the type compensator, and the driver circuit is there. That is the driver circuit, and finally the driving pulse is there, that is fed to the switch of the boost converter. Okay, so it's your inductor value and ESR of your inductor, and that capacitor is there. Okay, so it's the capacitor and ESR of the capacitor. So all the parameters are given. Okay, so from if you put those values, so you will directly get the transfer function. So I am telling you that boost converter having one problem, that means it having dealing with the non-minimum phase problem. Okay, so from this diagram you can see that it's in time response. Okay, it's in time response of your step up converter, means boost converter. So initially that zero. Okay, then you can see it goes negative side. Okay, around you can see minus zero point 0.3. Okay, so that means if it is in step response. Okay, if it is in step response, that unit step has no step response. Okay, so minus zero point 0.3 means it's 30%. Okay, nearer to the 30% phase delay is there. Okay, nearer to the 30%. Okay, so that's why I'm telling you, due to that negative means due to that undershoot path, you can say like then it's a non-minimum phase. So it's a non-minimum phase. That's why the undershoot is coming. Okay, so from the transfer function, previous transfer function, you can see one right up plane zero is there. Okay, so here you can see that one right up plane zero. Okay, that one right up plane zero is there. Okay, due to presence of this right up plane zero, due to that undershoot is coming. That's why it is written a right up plane zero presents the transfer function of the step up converter. Okay, the effect of non-minimum phase, the effect of non-minimum phase. Okay, non-minimum phase problem is occur the converter dynamics. Okay, so that's why the initial undershoot. That's why the initial undershoot. I am telling you is coming in the time response, and Bode plot has the sufficient phase lag at gain crossover frequency. Okay, so gain crossover frequency means here. Okay, so it's your gain crossover frequency, that 0 dB line. Na? So your gain response is cutting that 0 dB line. I think that point. Okay, so you can see at that point if you project. Okay, in your phase diagram. Okay, so in frequency domain, one is magnitude plot, another one is phase plot. Now, so in magnitude plot, okay, in magnitude plot, you can see when the 0 dB line is cutting. Okay, so when that your magnitude line is cutting to a 0 dB line, so you can see that phase delay is there nearer to the minus 270 degree, that point. Okay, so it is your nearer to your minus 270 degree. Okay, so sufficient phase lag. Okay, that's why you can say like the sufficient phase lag is observed. That I told my previous classes, I will able to show you to my simulation diagram. So it's my simulation diagram. So you can say from here. So due to presence of non-minimum phase, means one pole, one zero in the right half plane. That's why that phase delay is observed in the converter dynamics. So in type 2 compensator design, so I have one question. So do you have any class after my session? From 9, is there any class?
Yes, sir, we have.
So who is your concerned teacher?
Anup Kumar Panda, sir.
Okay. Panda sir class is there now. Okay. Actually, due to network issue, I'm not able to start my class at 8. I just logged in, but due to some issue. Okay, so I thought that I can complete the entire thing by this today's session. Okay, unfortunately, I'm not able to complete it. Okay, so uh, wait, and if possible, next Thursday. Okay, next Thursday, I will take 2 class. So if it is possible, so I can complete it. Okay, just another 5 minutes I am taking to wind up some of the portions. Okay. So that portion I have already discussed and in type 2 compensator. Okay, so in type 2 compensator and so you can follow this paper. So in details it is given. Okay, the paper is there. So design and implementation. That paper written here. The design and implementation of type 2 compensator here. That type 2 compensator design and implementation of type 2 compensator in DC-DC switch mode step up power supply. So here you can see that in previous diagram that I am telling you, so phase crossover that boost up to 70 degree for my consideration. You can see 0 dB line, so nearer to the value, so boost tester up to 70 degrees. So in type 2 compensator, what happened? You can see that one pole at origin, that pole is there in origin, then one zero, then one pole. So that one pole means minus 20, but degree lines are there. Then at that point, what happened? The zero is there. So due to the zero, that line is parallel to its 0 dB line. Okay. Then what happened? Another pole is there. So again it will be minus 20 dB, but detail line it is following. Okay, it's a Bode diagram of type 2 compensator, and second one is your phase diagram. Okay, phase plot. So here in step up converter is a right half plane 0, that is a non-minimum phase system, so it is difficult to PID compensate exhibit the good performance with line, load variations and parametric uncertainty. That's why type compensator you are using, it's a lead compensator within pole at origin. So it's provide you the fastest closed loop performance can be achieved with the minimal overshoot. Okay, so it's your structure, that's your structure of the transfer function. Okay, then the mathematical steps that I have already discussed. Okay, so phase boost, what happened, then mathematical steps. If you follow the paper, so you can get all those mathematical equations, everything. Okay, so it is given, so you can calculate that zero locations. Okay, that pole locations, we are able to find out the pole location, then zero locations. Okay, finally we will equate them. Okay, so taking an example, design example. Okay, so you got type 2 compensator design example. Okay, how practically it look like that. Facebook is considering 68 degree. It is your consideration, and you can say like then minus 18 dB deflection at 1 kilohertz. So you can replace all those value that you know that value of Facebook. Okay, so K value you can find out 80 pole location frequency, then by 2 plus 45 degree, directly coming that 5.14 kilohertz is there. Okay, it is your pole location, pole frequency, then zero frequency is there. Okay, so zero is placed at like that way, so you can find out the pole frequency, zero frequency, then if you replace all those value in the form, so you will get that type 3 compensator transfer function. That transfer function you have achieved here. Okay, transfer function is there. Then you can, in my last class I told you, so I have shown you some of the variation of your crossover frequency, what will be the effects of your converter dynamics. So here, for the standard case, you have considered that green line. Okay, that green line is there. So that green line, okay, that is your green line. So you are designed for 1000 1 kilohertz. So if you vary that value, okay, so first one is just below your 1300 hertz, another one is 200 hertz. So in transient response, you can observe for 2000 hertz. Okay, so in 2000 hertz, you can see that is overshoot is high. Okay, that red line, that overshoot is high. Okay, then if you reduce that value, that 2000 hertz to 300 hertz, so you can see it is not reaching to the steady state point. Okay, so and at 1000 is to give you the better one. Okay, so it is having minimal overshoot. Okay, how much of overshoot is there, that is given. So you get the changing of that crossover frequency that having direct effect on your transient response. Okay, so here you can see that percentage overshoot for 300 hertz, no overshoot is there. For 100,000 hertz, 4.52%. For 2000, it is to 11.2%. So increasing of crossover frequency, that may increasing of your overshoot percent. Okay, so also the rise time is low over here. Okay, rise time is low. Okay, but here rise time is quite more than of yours. So definitely overshoot is more means system performance it has affected. So phase margin you can see also very phase margin also 67.4 degree at 1000 hertz. Okay, so that's you are selecting the judicially all those values. Then gain crossover frequency. Okay, then phase gain margin, phase margin, all the thing you have studied. Okay, then you are changing that adjustment of the compensator gain. Okay, gain if you are increased. Okay, so gain if you are increased means you can see that overshooting is more. Okay, so gain means Z0. Okay, so red one is 1500, then G0 is 1000, then Z0 is 500. 500 that gives a very sluggish response, and 1000 gives you the optimum value, and 1500 gain is gives you more overshoot as well as the response is not so good. Okay, so that in table it is given. Okay, so that value comparison, and you can see that 1000 it gives you the better response. Okay, then all the values are reported over here. So if you observe that Crossover frequency is fixed. Okay, you are just changing the gain. So previous case the gain was fixed. You are changing the crossover frequency. Okay. So gain we have changed. So you can see that one. So I think all of you will understand. So in my next class I started with type C controller. Okay. So I'm